வீடியோல நம்ம ஒரு இம்பார்ட்டன்ட் ப்ராப்ளமா டிஸ்கஷன் பண்ண போறோம். ஸோ என்ன ப்ராப்ளம் அப்படின்னு பார்க்கலாம். Let I1 and I2 be the steady currents passing through a long horizontal wire X, Y, and PQ respectively. The wire PQ is fixed in horizontal plane, and the wire XY is allowed to move freely in vertical plane. Let the wire XY is in equilibrium at the height D over the parallel wire PQ as shown in the figure. Show that if the wire XY is slightly displaced and released, the executes simple harmonic motions. Also can be the time period of oscillations. Basically, they give two current carrying conductor. One is placed in horizontally fixed. PQ is placed horizontally, it is fixed. Like XY conductor is to be allowed to move in vertical plane, this plane like. Okay. Now we write the force experienced by this conductor. F is equal to mu naught I1 I2 L upon 2 pi R. R is replaced by D. So like F is equal to mu naught I1 I2 L upon 2 pi D. So which is the two parallel current carrying conductor experience a force. Like here the two conductor carrying a current in opposite directions. This conductor experience a force is like repulsive. Like here it is four directions. Here the conductor experience like downward force. In a particular distance, separations between D, that time this wire XY is comes to in equilibrium. In this equilibrium is comes to bring the downward gravitational force mg. So like we write F is equal to mg. In equilibrium position, these two equations can be equated. So how we come F is equal to K by D. So here mu naught I1 I2 L upon 2 pi is to be constant. So now we write K. So that's why we write F is equal to K upon D. Okay, finally K upon D is equal to mg, K is equal to mgd. So now the PQ plane is fixed. After that the vertical plane XY conductor should be moved. That time we will apply for the some external force. This is equal to the force experienced by this conductor minus downward force acting on this conductor. We should write in the form of F is equal to K upon D minus Y minus mg. Here we rewrite these equations, plug in these values of K. After that we get F is equal to mg into Y upon D minus Y. And then we write F is equal to mgy upon the denominator D is commonly take outside 1 minus Y by D. Here Y by D is very small, it should be neglected. Then F is equal to mg Y upon D. So now we compare these equations like Newton's second law of motion. F is equal to ma. Here the force is acting the opposite directions of oscillations of this plane. So that's why we write A is equal to minus F upon m. Now we should apply it or plug in these values of force. Finally we get minus G Y upon D. Here acceleration should be given in the form of simple harmonic motions. Ay is equal to minus omega square y. Here we want to find the omega square is equal to, in this y is taken out to left side and be equal. Now we get omega square is equal to minus a by y. Omega is equal to square root of g upon d. So how we come g upon d, or in these equations we plug in these values of accelerations a from here minus gy upon d. So finally we get omega is equal to square root of g upon d. So now we compare this omega on time period of oscillations like angular velocity or angular speed is equal to 2 pi upon time period of oscillations. Now we want to find the time period of oscillation. This term is comes to here, the omega is comes to here. So now we write d is equal to 2 pi upon omega. Omega is replaced by g by d. Finally, we get 2 pi square root of d upon g. This is like time period of oscillations for simple harmonic motions. Okay, thank you for watching this video.